Have you ever wondered how scientists build objects at the nanoscale? With its ever-increasing popularity and potential to reshape the way we live, it's likely you've already gained some awareness of nanotechnology as a field. But how is that technology created? Well, with all the varied nanotechnology applications comes an even greater selection of tools and methods used to fabricate, synthesize, or assemble nanostructures. Even creating a basic carbon nanotube is a process that could be done one of 4 different ways. Methods of growing or fabricating nanotubes range from arc discharge and chemical vapor synthesis to laser ablation. And if it wasn't complicated enough already, each method of fabricating nanotechnology typically has its own specialized set of tools and equipment. With so much variation, covering all the ways we build on the nanoscale, it's probably too general a topic to cover in one video. But what about something a little more specific? What about molecular machines? Do researchers and nanoengineers today have the tools to develop and build complex machines measuring only a few hundreds of atoms in any dimension? Could we create a blueprint of a molecular machine, say, a nanoscale speed-reducing gear, and drag and drop the atoms together to form our device? In the early 1980s, Gerd Binnig and Heinrich Rohrer developed the first scanning tunneling microscope, an achievement that would later earn them the Nobel Prize in Physics for 1986. The two developed the technology to view atomic structures with such clarity that single atoms on a surface could easily be seen and manipulated by the device. In 1990, researchers at IBM submitted a paper to the scientific journal Nature, detailing an experiment where single xenon atoms were rearranged on a nickel surface to spell out the IBM logo. The experiment seemed to herald a breakthrough in nanoassembly, and some scientists saw it as a significant step towards the realization of atomic-scale logic circuits and other nanoscale devices. But is the scanning tunneling microscope the answer to creating molecular machines? Well, to get a better idea of its capabilities, let's first try to gain a basic understanding of how the scanning tunneling microscope works. The scanning tunneling microscope, or S.T.M, is a type of probe microscope that utilizes the tunneling effect to detect nearby atoms and map their position onto a display. A probe microscope works differently than an optical or electron microscope in that it uses a physical probe or tip to feel the surface of a sample. At the atomic level, diffraction and other problems render traditional microscopes unsuitable for imaging. However, by using a fine enough tip, probe microscopes can offer researchers atomic-level precision in imaging and manipulation. Tunneling describes a phenomenon where quantum objects or particles go through a classically impenetrable barrier. In tunneling, having a smaller barrier increases the rate of tunneling exponentially. In our case, the quantum objects are electrons found in an atom's electron cloud, and the barrier is a very small voltage bias applied to the tip of the STM's probe. To obtain an image of a sample's atomic structure, the STM's tip scans over a surface at a distance of around 4 to 7 angstroms, or 0.4 to 0.7 nanometers. At this distance, tunneling allows electrons from the charged sample's surface to overcome the tip's voltage barrier and create an electric current between the surface and tip. The varying rates of electron tunneling are measured as the tip scans across the surface, and the data is then transmitted into an image, typically where areas of high current are represented as bright and areas of low current as dark. Using this technique, we can view the shape and position of atoms on a surface based off their electron clouds. So here's an oversimplified setup of an STM. As we just saw in that fantastic animation by Quantum Made Simple, linked below in the description, an STM scans over a material surface and determines atom position based off of current fluctuations. But STMs are more than just imaging devices. They can also manipulate atoms across the surface. Following the experiment by researchers at IBM, I have also prepared a nickel substrate and dosed it lightly with some xenon atoms. In order to keep my atoms stable and reduce outside particle contamination, I'm also operating my STM in an ultra-high vacuum state at a chilly 4 degrees Kelvin. In order to move the xenon around on my nickel surface, I need to get my probe tip to apply some force to the atoms. Fortunately, I found that by adjusting my position and tip voltage, I can take advantage of naturally occurring van der Waals and electrostatic forces to affect the atom just enough to slide it along the nickel surface. Throughout this moving process, the xenon atoms remain bound to the nickel surface, thus the extent of my manipulation is effectively kept to 2 dimensions. Using this process, I can rearrange the xenon atoms any way I want. And under the right conditions, they can remain in their positions for a few days. So going back to our question about whether STMs are a good device for building molecular machines, Now that we have a basic understanding of its mechanics, we might start to notice some problematic limitations. Although there have been many advancements to scanning probe microscopes, including one promising technique using atomic force microscope lithography and chemical treatment to create three-dimensional structures, they're probably not very well suited to creating nanoscale machines as we might envision them. Many techniques are limited to two-dimensional structures or lack enough stability to create complex parts. Additionally, it would take too long to assemble structures using this method for any realistic level of mass production. Creating a self-assembling molecular machine might be the first step, but the current technology in probe microscopy isn't there yet. But maybe we're looking in the wrong place. Interestingly, we already encounter and rely on complex molecular machines in our everyday lives. Technically, ribosomes are effective and widespread nanoassemblers which produce proteins in our own bodies. Kinesin and other motor proteins are working in highly functional molecular machines that play essential roles in cell activity. Perhaps our best hope for creating artificially made molecular machines will come from a convergence of naturally found biotechnology and nanotechnology tools. However, that line of thinking will be left for another video. Thanks for watching. I'm Jonathan Green, and when it comes to the pursuit of knowledge, Doseki said it best. So stay thirsty, my friends, and I'll see you next time.